Okay, yeah. Hi, everybody. I'm a postdoc who's been working with Carl on the gold fluid window project. And a year ago here, I talked about my results doing some structural mapping around the Pontiac. In the background of that, we were sort of dating some new zircon that we had collected over the course of mapping in the Pontiac. And so the focus of the gold fluid window is basically to show or explore the possible connection that was suggested by Pitcairn et al. In 2021 as to the potential source of gold along the major structures in the greenstone belts of the Superior Province. The Pontiac sediments were shown to be a plausible source of that gold as you went up in metamorphic grade. The ambient or the very low concentrations of gold that were present in the sediments got progressively lower, suggesting that maybe the gold could come from that. My job in all of this was to go and look for structural conduits for whatever those fluids were, and also map out the sedimentary belt and kind of test models for the tectonic genesis of the Pontiac, and because that's important to the overall thermal evolution and how you'd be generating these fluids. So everything I'm going to be talking about was published in this month's issue of Pitcairn Research. It's open access, so if you want the full story, there's some details that got cut out. You should be able to access that. Right, so we've talked a lot about the Abitibi yesterday, and so you guys are all probably familiar with most of this map. We're working in the Pontiac, which is this sort of wedge-shaped bit with quite a lot more of the metasediments, the turbidites that we often see draped along the major structures that divide up the Abitibi. And in particular, the Pontiac can sort of be divided into a northern metasedimentary dominated region. And then as you go south, you hit what basically a batholith of S-type granites that were interpreted to represent melts of those sediments that then came up and intruded the lower grade part of the package. One of the most important things about the Pontiac is that it's one of the few places in the Superior where we can see a continuous metamorphic gradient. So that tells us that we have different structural levels of the crust exposed, which means we can get a better sense of how things developed from a tectonic point of view. The Pontiac's also loaded with magmas, so we've had TTGs, Shanakitoids, and the aforementioned S-types intrude. And Adrian also showed that there was syn sedimentary volcanic activity in the western parts, the eastern parts of the Pontiac that was dominated by komatiites. So our goal here, the TTGs in the northern part of the Pontiac, this Opasatica gneiss, had previously been dated at 2765 million years, but just around it, and even to the south, as Carl just showed in the Grenville, most of the TTGs are younger than that. They're more Blake River age and younger. So we wanted to test that and see if this was in fact the correct age for this Pluton. So that's where we went. And also we investigated and mapped out a bit of the overlying volcanic sequence, and I'll tell you what we found there. So the two main components to the so-called Lac Opasatica igneous complex, which are distributed around Lac Opasatica, are a mainly komatiitic volcanic sequence that has been pretty well documented in the past. And then those sort of overlie the TTG gneiss that I mentioned. The new thing that we found during our mapping was a few horizons of felsic, fine-grained felsic material that are interweaved with basalts in the northern half of this volcanic sequence. And so those had been reported before, but maybe not recognized as a datable part of this pile. So we decided to go after those dates. So the Opasatica TTGs are pretty bog standard Archean TTGs. In this case, we do see locally it's got a more ferromagnesian component that's more diuretic. It has hornblende, whereas the normal gneiss is only composed of quartz, feldspar, biotite, and sometimes partially resorbed epidote and mica, which are pretty typical pretty typical to see in sort of the higher pressure TTGs in the Archean. And the first thing that told us that maybe we were on the right track with this was this deformation that we saw of this garnet bearing, so S-type dike that was folded around with an axial plane parallel to the nysosity, and the nysosity is also deflected by the dike. So that told us that nysosity was probably forming at the same time as that deformation was happening, and we know the age of the S-type intrusions, so it's likely that that deformation was younger, around 2660 or after. As for the volcanic sequence, here are the rhyolites, or at least the felsic vulcanites that we identified. They occur in sort of masses, isolated from any other lithotype, sometimes with what look to be slightly sheared porphyritic facies of the same rock unit, and then sometimes they, or most of the time rather, they're just sort of a planar unit in between different exposures of basalt. Whether or not they're flow facies or some kind of sill-like intrusion, subvolcanic intrusion, it'll tell us the same thing about the age of the basalts that they're part of. And the whole goal of this, as I mentioned, is to test models that had come before. So both of the previous structural models for the Pontiac from the 90s had looked, and they'd seen evidence of thrusting, or evidence that they interpreted as thrusting, as well as major décollement separating the volcanic sequence from the TTG gneiss. So this led them to interpret the gneiss as basement, and then the volcanic sequence and the metasediments were overriding that gneiss along in sort of a imbricate thrust setting. You can see the cross section here where you maybe get a little bit of thick skin thrusting. This is the gneiss interpreted to form majority of the hanging wall to the duplex structure that they interpreted there. And so I've only been here for a year. I know this has inspired some healthy discussions at these meetings, and this is basically the model we want to test. The Pontiac is certainly looks very similar to what you'd see in a Phanerozoic accretionary setting. You got the same lithotypes, and they're replete with these kind of precocious quartz and feldspar veins that have been dismembered within the foliation, and so this is what we're hoping to look at with our geochronology here. So it's important to know what you're dating. So here are just some geochemical summaries of the gneisses and the felsic rocks. They're quite similar from a major chemical standpoint. Doesn't necessarily mean they're related in any way, but overall they're both sodic. It would be more appropriate to refer to the rhyolites as soda rhyolites. They're about under 2% potassium, which leaves about 4 to 5% sodium in them in most cases. And this is, of course, the same situation for the TTGs. And then the TTGs themselves, from a trace element perspective, they're a little or a little depleted compared to your average Archean TTG. But overall, they follow the same general trend. They show a moderate depletion in the heavy rare earth elements, which again is consistent with the evidence that these are probably generated at depth from the resorption of the epidote, magmatic epidote and mica that we see. Conversely, the felsic rocks have very different rare earth element signatures. They have more of a flat to light europium anomaly, light negative europium anomaly to them. They look a little bit closer to what we see with the diorite gneisses in terms of their rare earth element profiles. So we dated zircons with the Laurentian lab, and the previous attempts to date the Opasatica gneiss had proven kind of challenging. There's a lot of scatter in the zircons. They're not very well behaved. Antoine Godet managed to get a date out of them, but you can see that there was quite a bit of scatter in the analyses he produced, and the date ended up being anchored to just 2 zircon analyses. And earlier in the 90s, Machado had tried to date the gneiss, but They were unsuccessful at obtaining an interpretable zircon date, and they went for titanite, which gave, well, the well-established timing of metamorphism and S-type intrusions at 2660. So we dated these via split stream at Laurentian using their triple quad and their Neptune Plus. Dated 4 TTG samples and 4 felsic vulcanite samples, as well as one of the diorite gneisses. And to try to overcome the problem with this scatter, we dated quite a bit of material. So we separated 100, 200 zircons from each sample, and Kirk Ross, he runs things overnight, so that let us collect quite a lot of data. And we used the trace elements that we got to filter through and pick sort of the most reliable data from among that. So we did see that same problem that was encountered before, at least with the TTGs. We ended up excluding quite a bit of data based on the trace element systematics, but I think we did end up in the end overcoming that problem. So remember, we dated probably between 100 and 150 spots for most of these, and well, we got quite a fewer dates that were not rejected on the basis of their trace element systematics. But what we see is that the tonalites are in fact dominantly around 2700 to 2687. So that's the same age as the Flavorian Pluton, same age as the youngest phases of the Round Lake batholith, same age as the Lac Opasatica tonalite, and same age as the Lac des Baies, as we know now. Roughly Blake River in age. One of our samples was a little bit older, without any real evidence for a signature in the same range, that 2700, 2687. So there may be, it may be composite. There's pulses of TTG intrusions of a similar age nearby as well. What else we see is that there are sometimes inherited cores. These tend to be in the range of 2745, 2748. This is the most common population that we see. And when we date, the dates that we got sort of confirm that our earlier suspicions based on the deformation we saw in the TTG gneiss. So those 2745 ages that we were seeing in the cores of some of those Opasatica zircon, they match up very well with the quite consistent ages we got off of the felsic volcanic unit. And this doesn't seem to be controlled. There's not too much of a structure in CL to the zircon. Cores and rims give typically ages that are within error of each other. There may be 2 separate pulses of volcanism, one around 2745 to 2740, and an older one between 2755 and 2750. But essentially, these all fall more or less within the range of the Picaud assemblage ages that are known throughout the Abitibi, and that's one of the oldest volcanic pulses that's known from the Abitibi. As for the diorite gneiss, so we were able to actually isolate a piece of the dioritic horizons within the tonalite gneiss exposures, and these gave a very consistent and fairly well-behaved zircon signature of 2745 plus minus 2. That's the same age as the rhyolites, essentially. And as I noted earlier, they have very similar rare earth element profiles. So these might be related somehow, given their ages and their similarities in trace elements. And importantly, it also tells us that there was something there before this time, because you had to have some kind of crust that these magmas could have come up through and intruded or extruded onto. As for a hint as to what that might be, Bruno mentioned this in his talk yesterday, but we do see inherited cores in these zircons as old as 2850 or thereabouts. And this is consistent with the observations, the isotope data from Carignan from 1993, who speculated there had to be material older than about 2.9 billion years below the Pontiac. And so realizing that our methods, that the inherited component of these zircons could easily be erroneously excluded or ignored because of our trace element filtering methods, that basically they're much more likely to have been altered or become metamixed later, and then we would have excluded them from our data. We sort of, I plotted them on this KDE plot at different levels of filtering. So much more generous than what we use to construct the Concordia plots. But generally we see in all cases that for the Opasatica tonalites, we see the strongest signal at the ages that we got from the Concordia, and that the inherited signal from the volcanics is by far the strongest. But as we go to lighter and lighter filtering approaches, we do see a more pronounced signal from that 2,800 million year age population. Conversely, the volcanics are quite consistent. They form a very prominent single peak. No matter how filtered you are, there's a very slight shoulder in that 2,800 million year range, but whether that's real or not, again, pay it some caution, given that these were rejected. They had high strontium, high iron, and they were quite discordant. Okay, so we have now felsic vulcanites around Lac Opasatica that record zircon, uranium, lead dates of about the same age as the Picot assemblage in the Abitibi. We have a much younger Opasatica TTG that is likely a composite pluton with a pulse at 2730 and 2700, 2690, and maybe 2745 if you want to include the diorite gneiss in with that. And that diorite gneiss seems to be about the same age as the felsic volcanics. And we see inheritance of that pre-2800 million year signature in the TTGs. One thing that I found interesting was that this identification of the Picot in the northwestern corner of the Pontiac, well, that's quite continuous with exposures of the Picot that are dominantly south of the Larder Lake Cadillac Fault as you go westward into the southwest Abitibi in the Swayze, Shining Tree areas, as well as around the Round Lake batholith. As well in the south, and John Ayers pointed this out in previous years, there's continuity of the much younger porcupine-aged volcanic rocks, the 2690 to 2685 rocks, that continues on into cobalt, which is generally considered to be part of the southwestern Abitibi exposed under the Huronian cover. So this seems to be telling us that if things have moved, they haven't moved much, or that there was some sort of continuity along this lineament that coincides with the Larder Lake Cadillac Fault as early as 2750. And whether that stayed that way or was later restored to that situation, what it seems to be pointing to is that the very similar geochronological records of the Pontiac and the Abitibi would tell us that these are likely parts of the same original crust, that the Pontiac was part of the Abitibi that is now covered by a thick sedimentary drape. How it got there, we don't fully know. I'm sure there's a lot of differing opinions on the precise mechanism to arrive there, but the idea is that it's more challenging to see the Pontiac as an exotic terrain that came in much later into the history of the region. It was likely developed alongside during the synvolcanic phases of the Abitibi. So, yeah, the Pontiac Group is deposited in a basin that seemingly was always magmatically active from TTGs to Santicatoids, especially if we take Carl's date from the Grenville province into account. Rather than the ancient TTG basement, the basement is in fact probably volcanic rocks of Picot age, similar to the Abitibi. That continuity along strike may indicate that the Abitibi, or the Pontiac, was always part of the Abitibi subprovince, and that we have the co-occurrence of 2745 intrusives and shallower expressions of that magmatism, which implies an autochtonous construction of the Pontiac subprovince, or at least of that mafic crust, or volcanic crust. So I want to quickly bring Isaac's results back into the picture because I think they were very important, and I want to talk about the necessary exhumation of the Pontiac. So back in the 90s, Powell argued that the isograds that were developed in the main metamorphism of the Abitibi cross-cut the Larder Lake Cadillac Fault, and this implies that metamorphism post-dated most of the displacement along that structure. So we have new data to confirm this, and we also have a date that gives us temporal constraints on that, a numerical constraint. So that's around 2657 the Pontiac and probably also in the Abitibi. Isaac showed that the Garnet zone records pressures up to 8 kilobars, and the storolite sillimanite zones record pressures of around 6.5 kilobars. So if we assume that the metamorphic pressure near the Larder Lake Cadillac Fault, or even just in the Abitibi, was only about 3.3 kilobars, that gives us quite a lot of implied exhumation within the Pontiac as well as across the different boundaries, both the Larder Lake Cadillac Fault itself from south to north, or east to west as you go into the southwestern Abitibi. We have maximum depths of exhumation implied to be 20 to 25 kilometers in the Pontiac, and maximum depths of 10 kilometers. So that's 10 to 15 kilometers of implied exhumation along these structures, or at least relative to these parts of the crust. So I think as we move forward, it's important to start probing that question, because most of the models go very deep into the convergent and the burial phases of building the Abitibi and the Superior Province, but exhumation is potentially equally as important and can tell us the stuff that we don't already know about the sort of orogenic phases, if you want to call it that. From what I've seen in the structures in the Pontiac, ductile thinning was probably an important contributor to this exhumation, but we know from Phanerozoic origins that ductile thinning can't be the only thing controlling that. And when you're in the middle crustal regions, usually what you're looking at is some sort of metamorphic core complex with low angle normal faults. And we haven't been able to identify these yet in any of these regions. So I think moving forward, it's important to pay attention to when these rocks are coming back up and the deformation that would have resulted from that, because we rarely see exhumation go completely without deformation to accompany it. So thanks, everybody.